sorry, I couldn't. Okay, so I'll just exit this quickly because sometimes if I don't accept this, then later it will cut it off. Yeah, and so yeah, sorry I couldn't be there in person since I'm just directly across the bay. But so today I want to tell you about some work I've been doing over the past maybe year or two now with a number of collaborators on trying to rethink jets in real world colliders such as the LHC or the EIC, as I'll mention, using some ideas motivated by developments in conformal field theory. And so in the talk today, I'll try and give kind of a general overview about how this is kind of shaping the way, at least I think about jet substructure. And then I'll focus on two particular examples, which have a little bit more of a kind of nuclear feel to them, namely the study of kind of these energy flow or jet shape observables on charged particles, and then the study of spin correlations. And feel free to ask questions or interrupt as I go. Okay, so just to set the kind of stage. So as everyone here, I think, judging by the audience, knows very well, when you collide protons, you get out these amazing event displays with sprays of radiation called jets. And something that's become quite popular over the last number of years is for experimentalists sitting off in infinity to study that radiation by measuring correlations in the energy coming off into their detectors at infinity. And so this can be done either through literal correlation functions or through the measurement of familiar kind of jet shapes or other jet substructure observables. And so this is not just something that one does for kind of entertainment, but a lot of the original motivation for this goes under the name of something called jet substructure, namely that if you have collisions at the LHC where you might produce some new particle, for example, a Higgs or some beyond the standard model physics, if it only decays hadronically, then one of the ways that you can detect that something new happened is that it will imprint something into the energy flow in your detector. And so if you're good at understanding the energy flow in QCD, then you can also detect that something unusual was happening inside your jet. And so this has really driven kind of a lot of progress both on the theory side and the experimental side. And so I'm not going to talk very much about this, or at least any of the details of the kind of beyond the standard model side of this, but I just want to emphasize that this is kind of now a very standard technique. And so a lot of the things I'll talk about, although they may be on a little bit on the theory side, will actually have kind of very concrete real world applications. And so although a lot of these techniques were kind of developed with this motivation of looking for beyond the standard model physics, jets will also play a central role at kind of any other collider that you have that has QCD. So for instance, EIC, heavy ions, et cetera, et cetera. And so there, the kind of goal might be a little bit different. So instead of looking for a Higgs or something, instead what you want to do is to just use some properties of the energy flow coming out to study the structure of QCD itself, either in the jet, its modifications in beyond the vacuum environment, or something about the actual nuclear structure of the colliding protons or nucleons. And so the hope here is that many of these kind of either observables or techniques developed to perform theoretical calculations developed in this kind of jet substructure context can also be applied here. And so with this as the kind of general motivation, what I want to do is kind of separate this talk into kind of three sections. So first, I'm going to give a general overview of this kind of new perspective on jet substructure, and in particular its relation with something called light ray operators, which I'll describe in some detail. And then I'll give two kind of concrete applications, namely this of kind of thinking in this way, namely the study of charged energy flow, and then understanding spin correlations, or in particular perturbative spin correlations within jets. And I think in particular, these two have kind of broader applications beyond the specific instances in which they've been developed. Okay, so jets and light ray operators. So part of this kind of program to rethink jets really requires you to go back and think at a kind of very basic level what you're actually doing when you perform a calculation in jet substructure. And so from a kind of very basic field theoretic perspective, what you're actually doing when an experimentalist has a calorimeter cell sitting off in their detector at infinity is you're studying certain matrix elements of what are called energy flow, or I'll refer to them as energy flow, and they have some other names depending on the particular community, such as ANEC or light ray operators. And so their definition is given right here. And so the way you should think of this is literally as just a kind of representation of a calorimeter cell. So you just take your stress tensor, you project it into some particular direction, you then move it off to infinity, and then you integrate over the time as just kind of the flux of energy goes through it. And so depending on your kind of background, you can either think of this as a literal kind of calorimeter cell, or as some kind of light ray operator sitting at null infinity in this Penrose diagram. And so it's non-local just because it has this integral over time, which makes it a bit different than maybe standard local operators that you're familiar with. And so correlation functions of these operators, such as this kind of shown here, kind of completely characterize the flow of energy in infinity, and anything you want or any observable you want can be constructed out of them. And this is just kind of tautologically true because this is all experimentalists can actually measure, put into kind of a theory land phrasing. And so once you have these kind of base objects, there's kind of two different paths one can take. So the first is the one that we normally take, which is to combine them in particular ways that we call jet shapes. And these are kind of familiar from all these jet substructure observables that people have been kind of talking about, like jet mass, thrust, angularities, et cetera, following essentially the seminal work of Eddie Farhi. And then there's a kind of second direction, which has been much less pursued on the more phenomenological side, which is just to take these base correlation functions themselves and study their behavior as actual observables instead of fully combining them. And so I should just say that if you know all of the correlation functions or all of the jet shape observables, these are completely equivalent descriptions. And there's kind of an infinite dimensional change of basis between the two, the exact kind of details of which don't matter, but any jet shape you can write as a sum over an infinite number of correlation functions. And so the kind of point is that this is actually an infinite sum. And so when you kind of move from one to the other, it kind of completely exchanges the way you think about the information. And so one thing which was kind of illustrated in this very important work of Maldacena and Hoffman a number of years ago was that if you work just in terms of these correlation functions themselves, then at least from the theory perspective, it kind of really simplifies your understanding of what's going on in jet substructure. And so what I want to kind of do in this talk is to pursue this kind of direction of thinking in terms of these base correlation functions and kind of make it into an actual experimental reality and illustrate that it gives kind of a number of new features where you can really understand things that you couldn't do before. And so I'll give some of these concrete examples, for example, calculations on charged energy flow and use of symmetries to really understand the structure, which you can only do when you work really in terms of these base correlation functions. Okay, so the reason why these correlation functions are particularly interesting is because you're often used to, or you're often interested in studying them in particular physical limits, right? So you're not interested in studying these when they're just kind of oriented at completely random angles. You're often interested either when you put a whole bunch of them together inside a single jet, which is what I'll call either the jet substructure or the collinear limit. And so this is what I'll kind of primarily focus on and has been the interest of kind of the LHC, because that's essentially what jet substructure is. And then there's the other limit where you take these at exactly back-to-back limits. And this is a bit more related to the EIC, and I'll just mention this kind of briefly. And these probe kind of very complementary physics, all just using these very simple correlation functions. Okay, so first what I wanted to do is discuss this kind of physics of the jet substructure limit and the light ray OPE. And so this is work with Hao Chen, who's an exceptional student, and my collaborator, Wajing Zhu. Okay, so the first question that one wants to ask is what makes jet substructure special if you were just so obviously it's interesting experimentally, but from a pure kind of field theory perspective, what makes it interesting? And so as I just mentioned, the reason why it's interesting is that you're interested in studying the behavior of either of these light ray operators or energy cells as you bring them together. So they're all kind of clustered inside a single jet. And so generically, you expect that as you bring operators together, they'll be governed by some operator product expansion. And so this is something which is familiar, for example, from the local operator product expansion, which describes scaling behavior in critical phenomena. Namely that if you have two operators, as you kind of bring them together, you can expand over some other set of non-local operators with some kind of scaling parameter in between them. And so it turns out that there also exists an operator product expansion as you bring calorimeter cells or light ray operators together. And so this was originally proposed by Hoffman and Malacina about 10 years ago. And I'll just write it kind of schematically like this. And so here, instead of kind of bringing the positions of operators together, you have a scaling in the angle as you bring, or kind of the angle between two calorimeter cells as you bring them together. And so you can kind of think abstractly as what you're doing is if you have some kind of generic configuration of energy deposited into a configuration of different energy cells, that you can expand this in terms of some more general energy cells as a sum in your detector. And so you can really think of these as kind of a detector operator product expansion between different calorimeter cells. And so this is extremely interesting if one can make it work in practice and in real world QCD, because instead of thinking about doing perturbative calculations and kind of quarks and gluons kind of flowing out towards your detector and having to do these hard calculations, their kind of structure of these correlation functions will be fixed essentially by symmetries and the structure of this particular operator product expansion. And in particular, one expects to see kind of universal scaling laws emerge, just like you do in critical phenomena. But here it's really just as you bring kind of detector cells together and apart. Okay, so in conformal field theories, this light ray operator is kind of a convergent and rigorously proven expansion. And in particular, it's an expansion in the twist of the light rays which appear. And so the thing that's very nice about this expansion for jet substructure is it's kind of the natural expansion because it's an expansion about the small angle limit. And so what that means is that even if we go away from these kind of very well understood kind of toy conformal field theories, we don't actually need to understand the full structure. For actual phenomenology, essentially you can truncate this and just take the first term in this expansion, which will determine kind of the leading behavior if you're in the small angle limit. And so just to kind of make this kind of, or to show that you can actually just, this becomes kind of a very concrete problem. If you restrict yourselves to the leading twist 2 operators in QCD, these are characterized by a spin J and a transverse spin, which you should just think of as the spin kind of in the plane perpendicular to the jet, being J equals 0, 2. And so in particular, there's kind of one operator which describes quarks, which aren't spinning, one operator which describes gluons, which aren't spinning, and then there's an operator which describes essentially spinning gluons. And so what's very nice in QCD is that if you kind of turn these into these light ray operators, then these 4 kind of pieces here, which I can organize into a vector, are the only thing which can ever appear in this iterative or in this OPE which I described. And so no matter kind of what you want to understand in your jet, everything is described by the scaling behavior of just these 4 operators. And so the exact detailed structure of this OPE doesn't really matter, but I'll just kind of, just to show that there's something actually concrete, essentially what happens is as you OPE together 2 of these energy flow operators, you just get one of these operators which I described before with the spin. So this is just this, the collinear spin in the twist 2 operators being J equals 3. And then as you iteratively OPE them together, you again just get these operators at just higher and higher values of the spin. And so what this means is that if you have some very complicated configuration of operators, you can just OPE them together and get out the scaling behavior of an essentially arbitrarily complicated configuration of these kind of correlators. And so this may seem kind of so far very abstract. And so now I want to show that you can actually just measure this scaling behavior that's predicted for these essentially arbitrarily complicated correlators directly in data. And so since the LHC has unpolarized beams, the simplest thing one can do is to just consider some correlator in a jet like this. It can be essentially an arbitrary shape, it doesn't matter. And what you want to do, or as you kind of scale this as a function of the size, so you can think of kind of zooming this in and out, you want to understand how the observable depends on the particular size of this correlator or its angular spread. And by performing this iterative OPE, you find that if you have n of these energy correlators that you're measuring, that the scaling is determined by a particular anomalous dimension, which I'll call gamma n plus 1. And so this these J values. And so essentially, as you go to higher and higher point correlators, you're just cutting out a particular value of the anomalous dimension at different values of the spin. And so to isolate this anomalous scaling, it's convenient experimentally to take the ratio of the scaling always normalized to a particular 2-point correlator. So for example, if I normalize the 3-point to the 2-point, I expect some scaling behavior as a function of the angle given by a kind of difference of these anomalous dimensions as I zoom the overall thing in and out. And so again, this kind of seems like just something that one can do off in theory land, but it turns out that you can actually just go out and measure this using open data. And so this is on the right is a kind of calculation of, so these are for up to 10-point correlators as you're scaling these in and out. And then on the left is a kind of measurement, where measurement should be taken in quotations, using CMS open data. And you can see in this particular kind of regime between here and here, which is the kind of perturbative regime in the jet, you get this kind of beautiful scaling behavior exactly as predicted by this OPE. And you can really do this for example, here up to 10-point correlators, which is something that you could just would be impossible if you just did it in perturbation theory, but it's really just kind of fixed by the symmetry structures of this OPE. And you can kind of verify in data these very basic properties of this operator product expansion and really see that the scaling behaves exactly as you would expect. And in particular, that is controlled by these particular spectrum of anomalous dimensions in QCD. And so I did not plot these on the same plot because this was unfolded by a theory collaborator of mine, but you can see that there's overall kind of very good agreement and the proper kind of comparison is something that's ongoing.
Ian, question?
Sure.
In your theoretical description, it was a very sort of abstract expression in terms of energy flow.
Yes.
Yet here you're talking about CMS jets, which is a very pragmatic, practical thing. You have,
exactly.
there are calorimeter cells that are inside the jet, and there are calorimeter cells that are outside the jet. So that's a very, that's a very down to earth sort of thing.
Perfect.
So what's a relation? I mean, how do, in practical terms, what do you mean when you say that the experimentalists can measure this?
Yeah. So perfect. So you can actually see it quite nicely. So let me draw like a big jet. So this is here. This was done with R equals 0.4 jets. And so you can see in this plot, so this is a function of the largest size between any of the correlators. So this is kind of the angular scale which sets the scaling. And so you can see that what happens here is that when R hits 0.4, which is the overall size of the jet, then you're kind of here you've restricted and only are considering the particles inside. And so that's why this behavior goes completely wonky once you hit the size of the jet. And then once you're only looking for angles inside or much smaller than the angle of the jet, you kind of immediately relax or quite immediately relax to this very nice scaling behavior that's expected because essentially your jet kind of radius is much bigger than the actual scales you're probing. And then what happens at this scale is you hit lambda QCD and then you just lose this description or this perturbative scaling behavior and you go to just non-perturbative behavior.
Oh, okay. Actually, I've noticed this as you're talking. I noticed it says anti-KT here. If I would do with KT jets, would that make a difference? I mean,
No.
you get different constituents. So is that? I'm just trying to understand. Your description is very, very beautiful and abstract. I'm just trying to understand how the practical world it imposes itself.
Yeah. So this is a very good. So it will definitely the behavior out here will definitely depend on the details of what you do. But this kind of small angle behavior will not. And so one other thing that I kind of didn't emphasize is because these are really correlating. So these you're detecting kind of energies at each of these. And so this essentially weights it. And so you do not get contributions from soft particles essentially. And so you're really just focusing on this collinear behavior at small angles. And so this scaling, the fact that there is some regime, so the exact kind of, if you change the kind of value of the R and stuff, the large angle behavior, you're away from this nice OPE, which is essentially universal, but then you'll move into some universal regime. And so that you can really think of this in exact analogy to kind of scaling behavior in condensed matter. That if you're, as you kind of move something towards its critical point, suddenly you'll go into this nice scaling behavior. And then as you move away, you'll get kind of more and more kind of global effects. And so as you go to bigger angle, it will matter whether you use KT, anti-KT, what the size of your jet is, all the details. But if you go to very small angles, you'll get into this beautiful kind of universal scaling behavior.
I guess the other aspect is the jet PT. These are very energetic jets. You want to be well away from what we in other circumstances call non-perturbative effects, hadronization effects, and so on.
Yes. So having the higher PT jet essentially just widens this regime where you have this nice scaling behavior. And so here I have it over essentially like 2 orders of magnitude, because I'm using here it's 500. And so as you go to smaller jets, so I should say also, so this depends. So if you do it for something like 2 or very low point correlators, you have a larger perturbative regime. Part of the reason why we went to high jets is we're doing something like n equals 10. So these are like 10-point configurations, and you get into the non-perturbative regime faster. If you go to much lower, then you wouldn't want to do something crazy like 10. You could just do 2 or 3, but there should still be some window where it's perturbative.
I guess that window is a lot smaller than EIC, but maybe we'll come back to that.
Yeah. But I think for like EIC, you would certainly not do something like 10. You do like 2 or 3. And you can see, although it's a bit cut off, these ones actually stay perturbative much deeper. It's just that once you go to 10 points, I mean, you really need 10 perturbative emissions, and that's, I mean, requires, you're essentially dividing 500 by 10, and that's why you get into problems faster.
Okay, good, thanks. Yeah, very clear, thanks.
Okay, any other questions on this one? Okay, perfect. And so this is kind of the nice universal scaling behavior of these correlators. And so the obvious other question you can ask is, at higher points, they also depend in a very non-trivial way on the actual shape of the correlators. So for example, if I have higher point correlators, in particular in this case, I have 3 correlators, I can put one at some position 0. I can take out the scaling behavior, which I discussed, to put the other at some position 1. And then I'll have some description of the shape in terms of a single complex variable z. And so this kind of z goes beyond, or this full shape dependence goes beyond what is standardly being discussed in jet substructure. And in particular, it measures, for example, aspects of the triple collinear splitting function, and really the detailed structure of, for example, quark or gluon jets. And so again, here, the details don't matter very much, but the kind of very nice thing is that once you work in terms of these energy or these correlation functions, they end up having very nice theoretical properties. And so you can really just derive these compact analytic expressions as a function of the shape. And so this is the result in n equals 4, which is not the real world. It's just, and you can derive a similar result in QCD, which is just a little bit uglier, and I don't want to write it on a single slide. But you can really kind of compute these very analytic results about the structure of multi-point correlation functions in jet substructure. And this is something where you can also kind of, it's not just, again, in theory land, but you can actually measure the full kind of shape dependence of these higher point correlators. And so this is, again, done by Patrick. So it should be taken with a grain of salt. And it's a little bit hard to visualize, but this is kind of a density plot of the cross section as a function of the shape of this triangle. So up here is kind of an equilateral. And then as I kind of decompress the triangle, and so you can really measure this full shape dependence, which is kind of mapping out the kind of higher point structure of energy flow within jets. And so kind of by formulating it in terms of these energy correlation functions, it really opens up these new kind of classes of calculations at higher points, and for these very complicated kind of universal scaling behaviors. Okay, so this will be now, so that's kind of the jet substructure aspect. And then I just wanted to briefly review how before getting to these kind of charged energy flow and spin correlations, how these observables also appear or how they have been used so far in EIC, just to show that it's not something kind of completely different, but it's actually, it can be phrased in a kind of similar language. And there has already been a little bit of work. So the case that's been studied in energy or at the EIC so far is for the case of back-to-back limits where you don't put these correlators together, but instead you move them essentially 180 degrees apart. And so here I'll be a little bit briefer because this is more just to illustrate that these have been used at the EIC. And this is also related to kind of more familiar physics of transverse momentum dependent PDFs and fragmentation. Okay, so
Ian, sorry, can I ask? Can I just ask a very quick question about
sure.
the jet substructure things? Like you showed, I think maybe on page 18 or so, you showed this expression in terms of z. Like, is that a little confused how I should think of this? Is this like a perturbative calculation, or is it just like from the scaling relations, or how,
so
how do you get that?
Yeah, so this is a perturbative result for the structure of this correlator. So I haven't this can be I'll mention a little bit later. So this can be, you can decompose it using this OPE into a sum over what are called conformal blocks. But here, this is just the perturbative result for this. So there should be, I've just kind of stripped all prefactors, but essentially this is coming from the leading 1 to 3 splitting functions, where then you put the 3 correlators on the 3 legs.
So is this, so what would be like what would you say is like the perturbative accuracy then of that expression?
Yeah, so this, so there's a whole bunch of, so to get the actual expression, this is also just the scale independent piece of this. So you have to add an overall, so this kind of describes the shape, and then you have to add an overall scaling. So I would say this is like, for this particular 3-point correlator, I would say this is like, it would be something like leading log accuracy. Or it's kind of like the first order at which it's non-vanishing. It just kind of, it depends how you want to compare it to other things. It just kind of, it's something that starts at a higher order, but this is kind of the first non-trivial order where it exists.
I see, but you would call that like a leading log summed result already, or is it somehow a fixed order result, or how should I think of this?
Yes, so if you write the full result, it's kind of different than standard because normally we don't have results that like normally when you go into the resummation regime, you're just kind of resumming in that variable. And so here you have some overall size of your, like, so here I've rescaled things, right? So I have 0, 1, and then the Z, which is some like cross ratio. So really you have the full, if you do the full thing, you can always rotate it. So it's like 0, I'll call it like X long, and then Z. And so what happens in the jet substructure limit is you have a resummation in X in this variable. So you'd have like very schematically like XL to the gamma, like the scaling behavior, which I showed earlier. And then you have some function, or then which I call G of Z and Z bar. And so you're kind of doing the resummation in a different variable than in this variable which describes the shape.
I see.
And so it's kind of just like a different, it's hard to like compare orders with the standard. So this scaling, because it's just dictated by these anomalous dimensions, like you know this to very high orders. And it's this shape dependent piece that isn't fully fixed by symmetries. And so this one you have to like kind of have to calculate it order by order. So essentially the symmetry is fully fixed, that it has some overall scaling, and then there's kind of some residual piece which is in terms of like cross ratios, which just you have to compute.
And the gamma, you say you know that to very high accuracy.
Yeah, because this is just the like collinear, these are just the like anomalous dimensions. So this you know to like 4 loops or whatever it is now from Mach and.
Oh, I see. Okay.
And so it's really this like scale independent piece which one needs to compute. And so that's why it's kind of like hard to compare so I would call it like leading log, but obviously there's a lot more in there than like a traditional like leading log calculation.
Right. Okay. Yeah, great. Thank you.
There is a question from Barbara, and she asked whether the scaling is because the correlation are scale independent of some range.
Yeah, so if by scale, it's essentially coming from, you can think of it as coming from a kind of conformal symmetry. And then there's an anomalous dimension, which is what's dictating this particular scaling. So one way of thinking about it, or what's actually happening, is you can kind of think of this correlator as living in this plane transverse to the jet. And then the scaling as a function of size is essentially dictated by the symmetries as you boost along the direction of the jet. And so there's just like you have anomalous dimensions controlling kind of scaling in normal things, this is essentially the anomalous dimension controlling the boosts.
Okay. I mean, the reason I was wondering is that the scaling behavior you showed looked to me very much like the scaling behavior of cumulants and just regular old particle production in heavy.
Yes, yeah. So I think some of the very early work on using conformal symmetry by like Polyakov many years ago was in terms of, he phrased it in terms of the cumulants. And so it's a similar underlying that you essentially have some kind of conformal or scale invariance, which essentially fixes it to be some form of power law behavior in terms of specific anomalous dimensions. And so it's a very similar thing going on.
I was just trying to connect that, being a dumb experimentalist, I was trying to connect that to what was actually going on as the jet fragments.
Yeah, so it's a little bit different here because this is really a scaling kind of as you bring two angles together. And so it's a little bit of a different physics, but the kind of reason that it leads to this scaling at the kind of very underlying limit is just that you have some scale invariance, or essentially like a symmetry, which forces it to be some power law form. But this is really kind of a scaling in the angle as you bring things together, which is a bit different than in kind of cumulants.
Well, you're going to do that with cumulants too, actually, by cutting up phase space into different size pieces and seeing when it all scales.
Yes. Yeah. And there's some, I mean, if you do like number correlators, which may be more close to cumulants, I mean, they have been studied as a function of size, as you're bringing kind of phase space bins together. And there it's very similar to what's appearing here. It's just what's happening here is kind of under perturbative control because you have this energy weighting.
Yeah.
But it's a kind of similar, yeah, it's a similar underlying phenomena. It's just kind of a little bit different in the technical details to kind of make it fully perturbative for these jet substructure analyses.
So I should think of it as an energy weighted angle correlation?
Yes, exactly.
Thanks.
Yeah. Okay. Okay, yeah, I think this is where I was. And so I'll just skip this one. Yeah, so actually let me just skip right to this. So how these have been used in DIS for the EIC. And so they're much less explored, but I just wanted to kind of advertise this work by my collaborator, Haitao Li, and some of his collaborators, Yanis Makris and Ivan Vitev. And so this was kind of some work they did trying to adapt these energy correlators to the case of DIS. And so here, what they kind of essentially what all that's being studied, instead of studying these kind of higher point or multi-point correlators, you can think of this as kind of being the most basic object which you can study is essentially a one-point correlator, where you just kind of have one energy detector shown here. And now because you have this incoming proton, you can work in the bright frame and correlate now the particular particle you observe with this proton. And so you're essentially measuring a one-point function, so you have one weighting of energy, and then the angle with the proton. And so the reason why this is nice is you can go to a particular regime, in particular where theta is approximately pi. And so then you're kind of far away from the kind of wide angle soft radiation and this anti-collinear radiation, which comes from the proton fragmenting. So essentially you don't want this particular stuff. You just want to focus on this jet. And you can do it by this, by going to this theta equals pi regime. And more generally, I think you could study higher point correlators in this particular limit if you wanted to. But so far, all that's been done is these 1-point correlators. And so here there's kind of just a factorization formula which allows you to express this result in terms of transverse momentum dependent parton distribution functions shown here, and some particular jet function which describes the particular spray of radiation which was shown in this particular picture here. And I'm being kind of purposefully brief. It's just I will come back to this a bit later as an application of some of the techniques which I'll show kind of emerge from this calculational framework that will allow one to kind of build on what was done here to do some what I think are quite interesting things using this particular formula. So this is just to flash it to show that something has been done at the EIC and that it's not something completely different, and I'll come back to it in a little bit, if that's okay. Okay, so hopefully that kind of gives a kind of picture about how one can start to think about jet substructure in terms of these energy correlators, and kind of reviews the kind of overall picture of what one is trying to do. And so now I wanted to kind of discuss two particular applications, which I think are quite interesting, which kind of, so our original motivation was to understand this connection with some of these theoretical techniques in conformal field theory. And then these kind of two applications, in particular, the ability to perform calculation on tracks and spin correlations kind of naturally just kind of fell out very easily from rethinking jets in this particular way. And so the first thing I want to discuss is how one can extend precision perturbative QCD calculations using what I'll refer to as track functions or generalized fragmentation functions, whose details I'll describe in a little bit. And this is collaboration with these particular people shown here. And so a lot of this kind of techniques for performing perturbative calculations are great, and you can do some very fancy things. But of course, improving precision, particularly for comparing with experiment, is not just about performing kind of higher and higher perturbative calculations. You also have to kind of develop techniques to perform new classes of calculations, which are perhaps more of interest to your experimental friends. And so many of the interesting measurements that are done on energy flow are performed on some restricted set of hadrons, which I'll call R. And so one of the examples, or some of the examples you can have in mind is, for example, you might want to use exclusively charged hadrons, which allows you to use tracking information. Or you might want to use something like strange hadrons if you want to measure the energy flow in strange particles to, for example, tag strange parton distribution functions. And so unfortunately, or fortunately, whenever you ask a question about the actual structure of the hadrons, which you want to measure, this is something which cannot be computed in perturbation theory. And so that's something which I kind of tried to illustrate in this picture, that in your perturbative calculation, you just have quarks and gluons. And so if you just measure the energy flow on those quarks and gluons, if you're asking a question about what's the energy flow in charged hadrons, you essentially need to be able to convert from your perturbative calculation to a calculation that actually encapsulates the kind of transition from quarks and gluons to whatever hadrons you're observing in your detector. And so one would like to use all these nice techniques which have been developed for perturbative calculations and extend them to be able to perform calculations on charged hadrons or whatever. And so just as two kind of applications, this is actually interesting. A first example is using tracking information at the kind of LHC. And so here are just some plots of jet substructure observables at the LHC. And so on the left are results without using tracks, and on the right are results using tracks. And so you can see, for example, that when you use tracks, you have extremely small uncertainties. And so this is very nice if you're wanting to probe very small angle energy flow within the jets. If you can use tracks, then this seems to work very well for the experimentalists. Although I, of course, do not claim to understand the details of that. And so unfortunately, there's no first principles calculation for these track observables. So the second potential application, which I think is quite interesting, is for these observables in DIS or the EIC. So there you're often interested in probing the kind of structure of the nucleon which is colliding. And so if you can, for example, perform flavor tagging in your final state jet. So for example, if you can measure the energy flow on strange hadrons, then this is naturally tracked back to a strange hadron coming from your proton or nucleon. And so it essentially allows a way of tagging the incoming quark and allows you to study, for example, these transverse momentum dependent particle distribution functions on, for example, strange hadrons. And so again, in this case, what you need to be able to compute is these the perturbative energy flow, but now on just strange hadrons. So how do you actually do this? So the way that you can do this is to use what are referred to as track functions. And so these are something which are very similar to standard fragmentation functions, except for instead of describing the energy deposited into a single hadron, these describe the total energy fraction going into all hadrons, so however an arbitrary number, with a particular property, which I called R, but which should be thought of as either, for example, charged particles or strange particles in the example which I gave. And so the definition doesn't really matter, but it's given there. And so you should really think of this as some non-perturbative object, just like a fragmentation function. And so you will not be able to compute it from first principles, but you can compute its perturbative evolution and how it appears in perturbative calculations. And so the reason why these are necessary as opposed to just standard fragmentation functions is if you want to compute these higher point correlation functions, then you cannot use a standard fragmentation, which just tells you the energy going into a single hadron. Okay. So why do these track functions and these energy correlators, which I described, kind of go seamlessly together? And so the reason is actually very simple. So these observables, which I described before, you essentially have the angles of your calorimeter, or they should really just be thought of as calorimeter cells. And so they're just essentially at some fixed angle, and you're just asking what is the average energy flowing through them, or you're just integrating over them. Well, so now if you want to switch to, for example, do a calculation on just charged particles, all you need to do is replace the total energy going through by the total energy on charged particles, which is essentially just multiplying your result by the first moment of these track functions, either for a quark going through your detector or for a gluon. And so essentially all that appears is not some non-perturbative function, like a complicated fragmentation function, but just an actual number, namely this particular first moment. And so as you if you put two detectors on top of each other, you'll get a second moment, for example, but you always just get a few of these moments appearing. And so this is extremely nice because it kind of simplifies us down to only have to understand these particular moments. And so again, I'll just write these moments here. And so unlike standard fragmentation functions, because these are now considering the total energy deposited into any number of hadrons that have these particular properties, these obey much more non-trivial renormalization group evolutions. And so in particular, if you consider the nth moment, it can mix with any number of products of lower moments shown here. And what one should think about is kind of if you have some third moment, that as your kind of particles fragment perturbatively, it can mix, for example, with three first moments as you split. And so this is something that's quite a bit more complicated than a standard fragmentation function. And so what we've actually done is to compute for the first time the evolution of these higher, or of moments of these generalized fragmentation functions at next to leading order, where they first start to become non-trivial, where you really have this mixing. And so just, again, I'm just showing kind of proof that we actually did this. This is just a kind of result for the third moment of the gluon and how it evolves. And so you can see these kind of mixing between this third moment and, for example, products of the lower moments here. And so this really allows us to perform kind of perturbative evolution of these track functions and perform calculations on tracks at higher loop orders. And so with this in hand, because essentially what this is doing is removing infrared poles from your calculation, you can start to perform higher loop calculations of these energy correlators on, for example, charged states. So this is for example, shown here is a plot of these 2-point energy correlators, where Z is the angle between the two detectors, or Z equals 1 minus cosine the angle over 2. And you can see in red is the calculation on tracks, and in blue is the standard calculation. And so these, and then on the right is another example on positively charged particles, just to kind of show you can do something different. And so these are calculations at order alpha s squared, so with 2 emissions. And so these match the state of the art for analytic event shapes, just period. But now you can do them on any subset of particles you want. So tracks, neutrals, stranges, or whatever you want. And you can really start to take advantage of these kind of state of the art perturbative calculations, but now do these on more complicated sets of final state hadrons. And so just to kind of go back to these 2 examples, which I showed you, and show that we can actually now get something out. So the first thing which I mentioned was these flavor tagging at the EIC. So here what you had to do was to compute the particular structure of this jet function shown here. And again, and so this is the result at 2-loop order. And the details do not matter at all. The only thing you should kind of notice is that this looks like some standard kind of perturbative result. The only difference is that now you have these first moments appearing in the result. So these are just some non-perturbative numbers which you just stick in, but everything else is just some nice kind of numbers which appear there. And so this kind of first moment is just coming because you're sticking a single one of these detectors in this jet. So the second application was for this jet substructure, the LHC, where you're typically measured in or interested in measuring these higher point correlator. So this is an example of the 2-loop. Again, these are just constants whose details don't matter. But here you're correlating 2 particles within the jet. And so you expect that now you get a product of 2 of these first moments, and then just a whole bunch more kind of nice numbers after them. And so you can see these are just appearing as all products of these first moments, and then just some nice perturbative constants coming out. And so this really allows us to kind of take advantage of all these nice very fancy perturbative techniques, but extend them to tracks or whatever other subsets of hadrons you want. Okay, and so in the last little bit, and I'll try and be brief here, so I don't go too much over time, I want to talk about a kind of another aspect which emerged out of this, namely the study of spin correlations in jets. And so on the jet stuff, or maybe I should ask if there's any questions on this section before moving on.
Yeah, may I ask a question? Can you go back to that expression where you had the evolution at NLO of the track function?
Yes.
Yeah, so you say allow precision track phenomenology at the LHC. I would turn it around and say, well, great expression. I don't have a reason to doubt it, but as an experimentalist, trust but verify. How would we actually verify this? What experiment what measurement would one do to actually observe this evolution? Yeah,
good. So for example, so you can do simpler things like just measuring. If you just want to measure the first moment, you can measure, so the first one's a bit less interesting, but you can just measure, like if, let's say you did E plus E minus, you could just measure the kind of 1-point function of energy flowing into your detector on charged particles and on normal particles. And then you would, as a function of energy, and then you would be able to see this evolution. So it's almost like what you do with fragmentation, where you measure like hadrons. And so indeed, if you just did it for a 1-point function, you should just observe the same scaling as you would for fragmentation. And so where things get interesting is you'd look at 2-point or higher correlators at different energies, and at different energies as a function of the angle. And if you did this, you would be able to detect this scaling. So it's very similar to what you'd be doing in like fragmentation type measurements.
So there, so you start with a calorimetrically reconstructed jet, and you look at the track constituents. In other words.
Exactly. Yes.
Well, you said E plus E minus, but at the LHC, that like.
Yeah. So at the LHC, you just do these all in jet substructure, right. And so there it's a bit less clean. You can still do it, but it's always going to be a mixture of these quark and gluon pieces. Mm-hmm. And so it may be a little bit harder to disentangle them. I think, for example, Ben has done these studies of quark and gluon jets at different rapidities, and there's definitely things one can do. But there you essentially just need to compare like some prediction for if you know the fraction of quark and gluon going into your jet. And then kind of stick it in and then compare with the results from, like, you'd essentially just leave these moments or the scaling of these moments as some floating pieces in your calculation. and then kind of stick in the fractions of quark and gluons going into your jet, and then look at the results.
Barbara has a question
Sure.
or comment.
Well, Ian just answered part of my question, because I was sitting here scratching my head wondering, okay, so this is a cool technique. What questions do I want to use it to answer? I guess quark versus gluon jets would be one. I guess what you would tell me is you want me to measure the delta R extent of the scaling and then the slope of the lines. And then presumably those would be different for light quarks and charm or bottom quarks, which we could measure the jets separately.
Yeah, so I think there's kind of two kind of angles with which one can approach this, whether or not you want to kind of use it or measure experimentally to probe this scaling, or whether you just want to use the ability to calculate observables on tracks to compare with more precise measurements. So again, I am not an experimentalist, and I think there's people on the call who can correct me. But so a lot of these jet substructure measurements where you're focused, like let's say you wanted to measure these 3-point correlators, which I discussed before.
Mm-hmm.
So if you're doing this inside a jet at the LHC, you're doing this at very small angles. And so it is my understanding that in these limits, the ability to perform the measurements precisely is kind of relies on the ability, or is much enhanced if you can use tracking information. And so that's kind of the example shown here is a particular plot where you can kind of compare the errors that you get with and without tracks. And so if you really want to do kind of precision measurements, and I think it would be much worse if you wanted to do like the 3-point correlator. And so in some sense, by using the ability to perform tracks, or the ability to perform measurements on tracks and compare with first principles calculation on tracks, kind of allows the opportunity that there could be a like theory calculation on top of here to allow kind of first principles measurements of these observables on tracks. And so I think that's kind of one application where you're using these track functions, is you're taking them for granted and using them as input to do kind of precision QCD measurements. And I think the same would be true of these kind of like flavor tagging, where you could do it on, you could assume you understand these track functions, which would mean you understand this particular piece. You could do this, for example, on strange hadrons. You could back out something about the strange TMD PDF if that was your goal. And so that's kind of, if you trust what we've done, then you can kind of back it out in this, you can kind of use these to have other physics goals. Of course, I think it's also interesting to directly experimentally measure their scalings. And so this is something much, or like, for example, it's quite analogous to Ben did these measurements of the running of the jet charge. And so there you just have some non-perturbative object, and you're kind of measuring its scaling and understanding if it is as predicted by the equations I kind of showed. And so it just kind of depends what the perspective. And for me, I personally trust that we understand how to do this perturbative evolution. And so it's kind of these physics goals, for example, the flavor tagging or these jet substructure measurements, where you can kind of be fed in and allow one to do some kind of other physics goals that excites me. But it kind of depends on what you're
yeah, thank you. That's very helpful. I always tend to gravitate towards the understanding the physics when the perturbative stops being relevant and you're just then crossing the boundary.
Yeah. So part of this is I come from kind of a perturbative world. And so that's why I want to use these, or I like the ability to perturbatively calculate with these, so I can kind of go over to and use them in jet substructure. But I think also, I mean, studying how these interface with non-perturbative corrections and actually measuring the scaling is, of course, also something very interesting. And so it's just kind of, what your personal tastes.
Cool.
Okay. And so I think I'm essentially at time. So maybe if I just have like 5 minutes, I'll briefly go through this application to spin correlations, if that is okay.
Yeah, please go ahead. Please go ahead. Yeah.
Okay. So again, because my kind of background is in this jet substructure and not in many other experiments where you already have polarized beams. And so people have done lots of interesting physics with polarization. So here we wanted to understand if one can do kind of, or understand polarization purely within jets. And some of these techniques can then immediately go over to cases where you have polarized beams, which simplify obviously what you have to do. So if you're doing something inside a, or if you have completely unpolarized external states, like at the LHC, the first time you can probe polarization is actually within a kind of higher point structure. So for example, if you measure one of these 3-point correlators, one way you can have access to the polarization, for example, of this intermediate gluon is to take 2 of these correlators to kind of bring them together and then to rotate them around each other by some angle phi. And because you have this third essentially reference detector, you'll now get some sensitivity to the polarization of this gluon with respect to this overall plane shown here. And so in particular, you'll get a kind of cos 2 phi interference pattern observed in the energy detector detector, which is kind of a probe of quantum interference directly in jet substructure. And so using our analytic results for this 3-point correlator, you can just kind of expand it out and look at what these actually look like. So just so that I'm not kind of making something up. And in particular, you can see that you really do get these kind of cos 2 phi pieces shown here. And so this is for kind of gluons, or so this is for a quark jet decaying into a gluon-gluon pair, or emitting a gluon pair. And then this piece is for a quark jet emitting a QQ bar pair. And so you can see they have opposite signs, but otherwise they both have this nice cos 2 phi modulation. And so one would now like to understand how to perform an all orders resummation of these kind of spin correlations within your jet. And so this is something which historically has been a little bit complicated from the standard QCD perspective, because you kind of get a whole bunch of gluons interfering with each other as you kind of build up your jet, and it's very complicated to keep track of. And so as a result, it's actually not in most standard parton showers. But it turns out to be something which kind of emerges extremely straightforward using the light ray OPE formalism, which I discussed earlier. And so again, I'm not going to discuss the actual details of what you do. I'll just kind of draw a picture. But if you have this 3-point correlator shown here in pink, essentially what you do is just follow this iterative OPE construction. So first you kind of just bring together 2 operators and replace them with one of these O3. And so these are the 2 which describe the spin. And so in particular, there's a piece in here which describes kind of spinning light ray operators. Then you just perform a second OPE, and you get the single O4 operator, who's where you now just compute its expectation value. And the point is that I just showed you much earlier these kind of concrete rules for how you do this OPE. And so you really just kind of sandwich these things together, and it's essentially a trivial algebraic result or procedure. And so what you get out is a kind of resummed formula for the structure of this azimuthal dependence in this particular limit. And so you can see kind of a normal jet substructure observable just has this kind of standard resummation structure shown here. And so here you now get on top of this nice kind of azimuthal structure. And so unfortunately, this is quite small inside these standard jets without doing anything more. But one kind of very nice thing which came out of our calculation is kind of before this, there were no analytic resummations incorporating these spin interference effects inside single jets. And so it turns out there's actually 2 groups which have since, or maybe in the last 6 months or so, both the Herwig and then this is the Pan-Scales collaboration by Gavin Salam, have implemented these spin correlations in parton showers. And so you can actually validate against the results that we have obtained from our analytic calculation to kind of make sure that these are properly incorporated in the parton shower. And so you can see kind of in pink is our analytic result shown there. And it exactly agrees with these blue dots. And so there's this kind of nice interplay between these analytic calculations and this parton shower development. And then you can obviously use parton showers in more general context to incorporate these spin interference effects wherever you want. And then I'll just essentially skip this. So one thing that's kind of very nice I'll just mention it in 1 minute, is because you have these essentially symmetry structures, you know that you don't, the kind of symmetries completely fix the structure of higher harmonics. And so you get not only cos 2 phi, but you get cos 4 phi, cos 6 phi, etc. And these are completely kind of fixed by essentially these boost symmetries and resum into particular hypergeometric functions. And so this is where kind of thinking in terms of these correlators really allows some kind of fancy techniques to be used to better understand these, but I'll just essentially skip that. Okay, and so just to summarize, so hopefully I convinced you that there's been quite significant recent progress in understanding jets using this particular idea of light ray operators coming from conformal field theory. And there's been significant interest also from the pure kind of conformal field theory people in developing these techniques. And they're quite excited that they can actually be used in jet substructure. And so by kind of rephrasing jets in the language of these light ray operators and these energy correlators, one can do some neat kind of things. And in particular, I highlighted the calculation of charged energy flow or tracks and spin correlations. And I think, so although these techniques are developed in the kind of jet substructure world, it's interesting to understand the kind of interplay with physics goals elsewhere and how they can be used more generally for understanding QCD. So thank you. And sorry for going a bit over time.
Oh no, thank you so much. I think we have a lot of interruptions, a lot of questions, and since we have already, have many questions, are there any other questions from the audience? Comments? Felix.
Hey, thanks a lot, Ian, for the very nice results. Like after what you mentioned before, I was wondering, could you say maybe again how you do the calculation, like at the very beginning where you said you have like calculations up to 10-point correlators?
Yes.
Could you say like what goes into that calculation? Because that still seems like rather difficult, right? Compared to say like your 3-point function that you mentioned, where the splitting function goes in and so on, right? So like, can you compute that to the same accuracy, or what goes into those things?
So what's shown, so what's shown here in this plot is the scaling as a function of size. So you can take a 10-point correlator of some arbitrary shape, but you're not asking the question of what is its full shape. You're just asking how it scales as a function of size.
So you mean that's the delta R, like the.
So if exactly. So like in this formula, so if I have a general correlator, it will have essentially some piece out front, which describes the overall scaling as a function of size. And then it will have some piece where you like describes the detailed shape. And so if you're only interested in the scaling as a function of size, then you can actually do it for any point. And it's kind of a single, so it just depends on the scaling, the variable, the overall size variable, and just goes to some anomalous dimension, right? And so you're not asking what is the shape dependence of the 10-point correlator, just how it scales. And so you can actually write it down for any number. So I can do it for like 1,000,000 points, and I can write you an analytic result for the scaling. So because it's just fixed by this particular symmetry. And then what?
So it doesn't need the gamma then, because I thought you said the gamma requires like the 3-loop splitting function, things like that.
Yeah, but it would be like if I wanted to do like the 1,000,000-point correlator, I would just take the 1,000,000th moment of the 3-loop splitting function. And so I know that that's something that I know analytically from Vermeer and Moult and friends. Right. And so those the kind of nice thing about these observables is you can just kind of make very general statements that like for any number of points, if I just scale the overall size, then I know how the cross section depends on that size. The thing that's more complicated is if you want the full shape dependence. And so that's something that currently we can only do. I mean, we're working more, but currently we only have a result for the 3-point. And so if you wanted to do the like 10-point and actually describe the full shape, it would first of all be a function of like 8 complex variables.
Right.
And so this would be something like insanely complicated. But the kind of the thing that at least I thought was neat from a standard perspective is you can kind of make some very general statement about how an essentially arbitrarily complicated correlator scales if you're just looking at the behavior as a function of size. And then you can actually just like, that's something you can do in open data, or Patrick can do, and you can measure very high point correlators and it actually, I mean, agrees.
I see. And so this delta R max, just to be sure, so that's the largest distance between any of the points. Is that
exactly? So to make it like just like an experimental thing that we can compare with Patrick, this delta R max is, if I take 10 points, then it would be like this. It's the biggest of any of them, and so I'm just taking one property, like a single variable that describes the overall shape, overall size of the correlator, but I do not care about the shape. And that's what allows to make kind of these very general statements. Yeah.
Oh yeah, very interesting. Thanks. Very cool.
Okay. Any other questions? Well,
if no one has a question, can I ask one more?
Yeah, go ahead. Yeah.
You can ask me.
Sorry. Like you mentioned at the end, like these spin correlations, right? And that you compare, or that I don't know, others compare to, these parton showers.
Yes.
I was wondering, so at least from my understanding was that Herwig or these showers have been around for a while, right? They always had spin correlations implemented in some way, right? So I was wondering, did they change something about their code, or did they just compare now
they have
to your results for the first time?
So Herwig has some like approximation for it, but the full spin correlations was only implemented, like this was done by like Peter Richardson, and is in the updated version like maybe like 6 months ago or so now. And so there it actually has, before there's some approximation, which I think gets them right in the soft limit or something, but the actual full, so there's this algorithm of Collins and Knowles for how to implement these in parton showers, and this was done in like 80 or something. Yeah, and then it was just never implemented. And so it was implemented by Peter Richardson and Herwig about 6 months ago, and then the PanScales people also did it. And so, I mean, I think I think someone could have implemented it before, but I think now, I mean, one can actually compare with analytic calculations.
So you say before they had like something approximate.
They have something approximate, paper, and basically. These people, I've not seen a comparison of like the approximate with the full. That's something, I mean, it would be interesting to do now, but I mean, this was like this PanScales paper, I think was just like 2 months ago. So there's kind of this very recent interest in this, but it's just not explored.
Okay.
And I think part of the interest in this is that if you're only measuring like 2 point or like something like mass in jet substructure, it doesn't matter because you don't have spin correlations. And so, but if you start asking questions about like 3-point correlators and higher, which are being used now quite a bit, then you actually need to start getting these things correct. And so I think that was, and you actually need to, if you want to kind of say you have an actual NLL parton shower, which is Gavin Salam's motivation, I mean, then you need to incorporate them. And so the nice thing is we kind of now, just as we kind of published ours just before they were, or just as they were kind of implementing. And so they were actually able to just like compare and see that it all kind of works out. And so there's kind of a nice interplay. But I think it would be interesting to understand what, like, how good Herwig's approximation gets or what Pythia is doing. And that's something that in principle, these people can, I mean, it should be easy to answer.
Right. Okay, yeah, cool. Thanks, very interesting.
Okay, well, I would like to thank Ian again for this very nice talk. And I hope to see you next week for another his seminar.
Thanks, Ian.
Okay. Yeah, thanks a lot for the invitation.
Bye-bye. Thank you, bye-bye.